Hello guys, this is Saksham Jain and I welcome you all to the Future Camp. So in this video we will be discussing everything you need to know about overfitting and underfitting. So without wasting any time, let's get started. So let us suppose that I am building a model that is able to predict whether the object that is kept in front of them is a ball or not. So first of all, I made a model in such a way that there is only one parameter or feature. That is, my model only sees on the basis of only one parameter, that is whether the object in front of it is spherical or not. So spherical is my parameter or feature. Now suppose that I put this object in front of my model. This is a lemon. You can see it is spherical in shape. Now since it is spherical in shape, my model is going to consider it as a ball. But we know it is not a ball. Now here is a second object. This is a tomato. We know that it is not a ball, but since it is spherical, just because it is spherical, my model is going to consider it as a ball. And in the third case, I have a real ball with me, and since it is also spherical in shape, my model is going to consider it as a ball. So here you saw that even though the things were not ball, even though many things were not ball, but since because of one feature, because they were spherical, my model considered them to be a ball. So now what I did is I learned from my mistake and I created a new model. In case of a new model, the model basically sees four features. That is whether the object is spherical in shape, is it inedible, is it playable, that is you can play with it, and whether it is of red color or not. Now suppose I bring this lemon in front of my model. Here it is spherical in shape. So yes, it is spherical in shape. But is it inedible? No, it is perfectly edible. You can eat a lemon. So here one feature is not matching, and also it is not playable. Lemon is a vegetable. It is basically food. You cannot play with food items. So yeah, it is not playable. So since, and also it is not of red color, since there are three features that are not matching, here I can say that my model is not going to classify this as a ball. Very good. In the second case, I'm bringing a tomato in front of my model. Here it is spherical in shape. Great. But it is edible. It is not inedible. It is edible. You can eat tomato. So yeah, this feature is not present. And is it playable? You cannot play with food items. So yeah, this feature is also not present. And is it red in color? Yes, it is red in color. But since two features are not matching, my model is not going to consider it as a ball. Now in the third and the last case, here it is spherical in shape. Very good. It is inedible. You cannot eat a ball. It is perfectly inedible. So yeah, this feature is also magic. Is it playable? Of course it is playable. That's why it is a ball. So yeah, you can play with it. So this feature is also matching. But is it of red color? No, it is of yellow color. So since just because this ball is not of a red color, my model is not going to consider it as a ball. So here again, I learned from a mistake and I removed the unnecessary features. That is the features that are not required. So I removed the feature of presence of red color. Now finally, if I show any kind of ball, basically this ball again, so it is spherical, it is inedible, and it is playable. So yes, now my model is going to consider it as a ball. So here the first case represented the case of underfitting. The first case, that is the presence of only one feature that was of spherical, was case of underfitting. That is, my model shows very poor accuracy in case of training as well as testing data. The second case, that is presence of four features, spherical, inedible, playable, and red color, case of overfitting. Here my model pays very much high attention towards the training data, but it performs very poorly in case of testing data. Here in case of overfitting, my model is not generalized. It is not able to handle any kind of general data. It is good for only specific data, but not good for general category of data. It is not good for any random data. But in the third case, my third case represented a case of a generalized model, a good model, a model having a balance between overfitting and underfitting. So yeah, the third case represented the case of a balanced model. So that was all the feeling or intuition that you need to know before understanding the concept of overfitting and underfitting. So finally, let us understand what does overfitting and underfitting mean. Overfitting means that the model is performing very good, or I can say that my model is showing pretty high accuracy, not pretty high, a very high accuracy in case of my training data set. But that model performs very poorly. The model is not able to perform very good in case of a testing data or any kind of a random data. My model is not generalized. It has paid special attention towards the training data. So therefore it is good for only training data. It is not good for testing or any kind of random data. My model is generalized. If I talk in terms of bias and variance, if you don't remember the concept of bias and variance, then you can check my previous video. It was all about everything you need to know about bias and variance. So if I talk in terms of bias and variance, then in case of overfitting, my model must be having high variance and low bias. And in case of underfitting, my model must be having low variance and high bias. In underfitting, my model is not good for anything. My model is shows poor performance in case of testing data as well as training data. My model has poor generalization in training and testing. Basically, in everything, my model shows very poor accuracy. My model is not generalized. In overfitting, there are excess number of features. My model is high in complexity. My variance is too much high. But in case of underfitting, my variance is low and my bias is high. My model complexity is extremely low. That is, my model is not having a good number of features to predict something. Now let us use some graphical representation in order to understand underfitting and overfitting in a much more deeper level. So here I have taken two cases. The first row represents the case of regression and the second row represents the case of classification. In the first row, here you can see that all my data points here, all the dots represent my data points, that is my training data points. What does overfitting do? In overfitting, my model tries to fit through each and every of the data point in the training data set. So my model's prediction will look like this in case of a training data. Here you can see that my model is trying to fit through each and every data point. But in case of testing data, for example, any random kind of data appears. Since my model is not generalized, since my model does not follow any kind of specific pattern, it was good only for the training data. Here now, if these red dots represent my testing data, my model does not know what to do. It will be showing, it will keep on predicting any random values which will be far from my actual values. So yeah, in case of overfitting, my model is good for training. My model shows high accuracy in case of training, but in case of testing, my model's accuracy is pretty much low. In case of underfitting, you can see my model's prediction can be anything. It can be this line, it can be this line, it can be this line, it can be any line. My model does not care about the data points. It goes along its own flow. It does not care where the data points are lining. In case of underfitting, my model shows extremely poor accuracy in training as well as in testing data set. But in good generalized model, my model shows a perfect balance between overfitting and underfitting. Even though you can see in the case of generalized model, my model does not try to fit through each and every data point. In case of generalized, you can see that my model, even though it's not passing through each and every data point, but you can also see that my model's prediction are not far from all the data points. It passes through it basically tries to pass through all the data points or tries to pass closer through all the data points. So in case of good model, my model shows great accuracy in training as well as in testing data. In case of regression, you can see that basically I've drawn two symbols, cross and the dots. These are not dots, you can say they are color filled circles. So I've used two different shapes in order to classify my objects. My cross can be one category of object and my circle can be another category of object. For example, my cross can be representing the cats and my circle can be representing the dogs. So here in case of overfitting, what the model will do, it will try to classify perfectly. You can see that it tries to pass through all the data points. So yeah, This is a case of overfitting. If any random data appears, my model is not able to my model is not able to handle it because it does not follow any pattern. My model was good only for the training data set. In case of underfitting, my model does not care. It is a total opposite of overfitting. Here my line can be this, my line can be this. Basically it has nothing to do with classification. In underfitting, my model does not perform good in any place. But in case of good model, what my model will look like, my model can look like this, something like this. Here it will be able to perform good for future data points also. And in training, it might not be good as the overfitting model, but it will be pretty much good in case of a testing data set. Now here, for example, this is a graph. Along the y-axis there is my predicted error, and along the x-axis it shows my model complexity, my increasing model complexity or algorithm complexity. Suppose my red dot here represents my prediction error in case of my testing data. So as I continue to train my model and increase the complexity, my model will show decreased prediction error. I continue to increase my model complexity, I continue to train, and so on. But after a certain point, but after a certain level of model complexity, my prediction error will not go down. It will now try to increase. As I increase the model complexity, as I go towards the case of overfitting, my model will increase, and so on. Now let's take the case of training data. So let us suppose this blue dot represents my training data. So as I continue to train my model, increase the complexity, my prediction error will decrease. In case of training error, my prediction error will decrease. I increase the model complexity even more, and even now my prediction error will decrease and will try to approach zero. It will not be equal to zero, but it will try to approach zero. This was case for testing data, and the case below is for training. So let me draw a line. Here you can see that after this point, my model's prediction error will not continue to decrease, it will rather increase. So let us draw a line here. So everything on the left side of this line represents the case of underfitting, and everything on the right of this black line represents overfitting, and this black line represents a perfect case of a balanced model, a good model, a generalized model. So everything on the left of this line will be my underfitting case, on the right will be my overfitting, and this line itself is a case of a generalized model, a good model, because here my training error is also low and my testing error is also at its lowest form. Now let us discuss some ways to prevent overfitting. So overfitting can be prevented by cross-validation, training with more data. So I can train with more data so that my model can see more patterns, more features. It can train itself on more features so that it can be more generalized. I can remove some excessive features that are irrelevant for my model's accuracy. I can do some regularization techniques, for example, L1, L2, that is my lasso and ridge. And I can perform some ensembling techniques, and I can also do early stopping. So what is early stopping? Here in the previous graph, what I did was, what I can do is, here once my model's training reaches here at this point, I can stop the training so that my model does not train anymore and it is at its lowest prediction error. So this is known as early stopping. That is for example, in this case, stopping at this point. And what is cross-validation? So cross-validation means that splitting your training dataset into multiple train test splits. Now let us discuss how we can prevent the underfitting. So to prevent underfitting, what you can do is you can train your model with more data so that it can see more features, so that it can analyze more patterns. So yeah, you can train your model with more data. You can use some more features, more relevant features, more good features that are good for my model. for my training as well as testing. You can basically add more features or parameters. And the third is you can create more powerful models, or you can change your algorithm. So these are the three methods to prevent underfitting. So that was all for today, guys. In the next video, we will be dealing with logistic regression. So we will meet in the next video. Until then, bye bye.